Hello, I'm Neeraj Kumar. Today I will try to explain the concept of quantizations, like why we use quantizations in large language model based on patients. So generally what happens when we train the large language model, the trained weights are stored in the form of floating point matrix. For example, you can see this very simple 3 by 3 matrix. Just assume that if we have just 3 by 3 matrix, then floating point number having 32 bit size will take, we have total 3 columns, 3 rows, so total 9 elements is taking actually 32 by 8, 4 bytes each. So means each element is taking 4 byte. So total 9 element will take the 36 bytes of memory. So in this case, this small 3 by 3 matrix which uses the floating point number, 32 bit floating point number or 4 byte floating point number, consumes 36 bytes. So you can assume the situation if you use the model having billions or trillions of parameters. You can imagine the size of the trained model. Now we try to map this matrix through some 8-bit integer matrix. Means we are doing quantizations. So 8-bit means 1 byte. So in that case, the final matrix will cover just 9 bytes of memory. Means you are saving 75% of the memory resources. Now how beneficial this is? Suppose there is a case 1. You have a genuine original large language models saved in a floating point number and whose size is 25 GB. That is case 1. Now there is a case 2. Here your original size of floating point database saved model is 100 GB. Now you quantize this and make it 25 GB representation, and you do operations in both cases, case 1 and case 2. Means through prompt, like you can ask any type of questions to test the efficiency of both kind of language models, like different types of prompt engineering. You will find that after quantizations, C2 is performing better than C1. So because you are using more efficient or more knowledgeable models with less memory resources, that's why we are preferring quantized model in place of very small language models or smaller versions of large language models. So this is the reason. But for this, you have to follow some of the process. Now another thing is like how the systems are working. So once you quantize the floating point number into integer format, you can do all the operations like inferencing, prompt engineering, all those things that will work and on this quantized matrix. After quantizations, when you generate the results, it will go apply the dequantization process. So if you apply the proper process to quantize this, then dequantization matrix will not result in significant error. For example, once we quantize this matrix, it converted into this 3 by 3 matrix. Here you can see that 1.2 is converted into 44, 2.3 converted into 85, like that. So after conversion, when we dequantize, 44 is again converted into 1.2015, but actually it was 1.2. So difference is minus 0.0015. Means the difference is too low. That's why it will not affect the quality of results, and several times you will get better results in C2 with respect to C1. Now the things are like, what are the things that we have to follow in the entire process? So first and important part is scaling factor. We should have a proper scaling factor. Otherwise, mapping from floating point to integer matrix, floating point matrix to integer matrix will not be a proper matrix, and the reconstruction will not give the correct result. You can see through some example that what will happen. For example, this is a quantization technique. So in quantizations, what we do, we just round the value. So suppose here our value is minus 1.2, and we have no scaling factor. Just we are using some 0 point. Suppose our 0 point is something just did. So after rounding, because we have no scaling factor, it will be 1, minus 1. Again, suppose we have another value, that is, suppose in place of 1.5, suppose it is like 1.4. Then again rounding will be minus 1. What will happen? We will lose some informations in lower precision cases. So in that case, suppose it is minus 1.5 and it is minus 1.4. In that case, both conversion will be minus 45 and minus 45. And finally, it will result in minus 1.17, means after dequantizations, and minus 1.17 instead of this. So in that case, you can see that how much error will be. Means compared to this, you will get very high error. Means your reconstructions will not work properly. So that's why we do proper scaling factor calculations. Means we use the proper scaling factor in the conversion from actual matrix to quantized matrix, quantized integer matrix. Second point is zero factor or 0 point. Suppose we don't use the 0 point, then what will happen? Generally what happens, we think that suppose data is in the form of positive and negative format, especially this affects here. So in that case, in a real scenario, we consider that this is our 0 and all number that is greater than 0 will come in this side, and all number less than minus less than 0 will come under this side. But actually what happens, in a particular representations, the 0 point may be different. In some cases, 0 points may be at this place. In some cases, 0 point may be at this place. And in some cases, 0 points may be at this place also. So in that case, if you don't have a 0 point, if you are not using 0 point, then system will by default consider this as a 0 point for all cases. In that case, when you dequantize, you will not get the original matrix. You will be too far from the actual original matrix. Another problem that you will get, for example, suppose same kind of things like here. So you are doing the quantizations and you have you are using some number, some scaling factor. Means in that case, quantizations without 0 factor, you will quantize like this. Means x divided by scaling factor. So your x is suppose 1.2 and scaling factor is suppose 1.0261, like 0267, like we got here. So in that case, you will get some number, and for negative you will get negative number. So in that case, what happens? Generally, without 0 point or without some definitions, the integer 8 generally represents 0 to 255 range. So in that case, all negative value will be clipped. Means you will lose all those values. Another thing is like I discussed here, with a small precision kind of value. So in that case, if your 0 is here, then a lot of small precision values that in this side you will lose, because your 0 will be considered here if you don't have 0 point. So entire system will not work. Means if you are getting error in the reconstructions and your reconstructed matrix is too far from your actual floating point matrix, then system will not work, because all large language model generally use this output matrix to recall that what kind of value represents what kind of text. So based on that, it maps their vocabulary and give you the text, or sometimes images, or sometimes sound in the case of multimodal cases. So if you are not able to reconstruct it properly, then the output will be different and it may deviate from your questions. So now, so these are the few things that we can summarize it like that. So 0 point generally supports the negative value, maintain the precision, means for example here I said here it is 0, so maintain the precision across 0 and gives the effective representations of floating point to quantized integer format. So these are the key things. Now we will go through some more deeper steps. So now let us try to go through a simple explanations like how we can quantize or dequantize. So this is very important, simple. So first we will calculate the scaling factor. So S equal to R max and R min. So in that case, in this matrix, our R min is minus 3.4, smallest value. R max is range maxima is like, means maximum of this range is 3.4, like this is the maximum. Similarly, if we want to convert into 3-bit signed integers, then value will range from minus 128 to 127. So in that case, Q minimum will be minus 128, Q max will be 127. Now use it to calculate the scaling factor. So R max is 3.4. 3.4 minus 3.4, because R min is negative, divided by Q max is our 127 minus 128. So it is like 6.8 divided by 255. So if you take the revision, I got the result 0.0267. Okay. So it is near to 0.0267. Just to check it. So this is the value. Similarly, 0 point Z will be computed like round of R minimum, minus R minimum is minus 3.4 divided by S. So our scaling factor is this. So it is 0.0267 plus Q minima. So Q minimum is minus 128. Then if you calculate, you will get round minus round plus 1, you will get 127.34 minus 128. So rounding, after rounding you will get minus 1. Means for this point, if you consider the positive and negative and positive, then you will find that this 0 is not the 0 for this. Its 0 point is lying at minus 1. So this is actual 0 for this point, for this representation. So now The next thing is like a quantization, how to do the quantization. So if you want to do the quantizations for 1.2, like Q 1.2, it is very easy. Now it is just like a formula based on computations. So it is 1.2 divided by 0.0267 because this is our scale, plus z. Z is our -1. So if you compute everything, you will find it is 44. So you will get value like this. Again, if you want to dequantize this 44, then you will get, you have to apply this like Q minus Z. So you will take 44 minus, what is your Z? -1. That is calculated here, into S is scaling factor, that is 0.0267. So if you solve it, you will find that it is something around 1.2015. So this is dequantized value, this is quantized value. So you will find that the dequantized value is very much near to the actual quantized value. So it will not significantly affect the quality of the result. Now the things are like, this is the basics of quantizations, dequantizations, how it is used in the large language model cases. But there are a lot of different varieties of quantizations. Sometimes they use instead of 8-bit, they are using some lower bit quantizations also. So this is also possible. But in that case, this difference matrix will be different. Means the gap between actual and dequantized matrices will little increase. So if you want to maintain the good performance, balance between good performance, then you have to maintain the minimum difference between the actual representation floating point and dequantized floating point representations. So in that way, a lot of people proposed a lot of different kind of algorithms. For example, static, if you are going to calculate everything on the way, then dynamic, and a lot of different ways, like if you want to do the selective kind of quantization, dequantizations, if you want to achieve some goal through the quantizations. So based on all different aspects, people develop, or researchers have developed a lot of different varieties of quantization techniques. So in the next tutorials, I will try to go through some of the useful concepts, but I think you will get the intuitions like how people are thinking in this area. So what kind of intuitions are required in such kind of research work. So hope you have enjoyed this tutorial. So thanks for watching.